Early start.
What's the occasion?
I'm just going for it.
Oh.
I'm getting all ready for it.
Tell them it's against your religion.
Just like people in the Navy. Or you can say, oh, my face breaks out if I shave. Remember those guys?
Is he coming back?
I assume so.
Gary, you ready? Okay, let's get started. Let me have your attention, please. Let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is Dr. David Holcomb. He is a senior research staff member in the Nuclear Science and Technology Division of the Oak Ridge National Laboratory. David received a BS in Engineering Science at Colorado State University in 1987, and then an MS in Nuclear Engineering from Ohio State University in 1990, and again, PhD from Ohio State in 1992. He joined ORNL in 1993 as part of the Instrumentation Controls Division, which is now part of the Nuclear Science and Technology Division at Oak Ridge. The title of his presentations today is Modern Nuclear Power Instrumentation and Controls Research Directions. Ladies and gentlemen, please welcome Dr. David Holcomb.
Good afternoon, everyone. It's a privilege to talk to you this afternoon. What I'm going to talk to you about represents part of an ongoing process between several of the DOE laboratories and other interested parties about looking at where does the nuclear power instrumentation controls research really need to go in the next few years, and how can this couple into the national research strategy? And at the moment, I'll talk about a little bit more about how we're going about bringing this type of a cross-cut program into DOE's and NRC's research pictures. And we're trying to and then I'll give you some updates on some of the interesting technologies that the NRC and the DOE have been pursuing in the last few years in nuclear power INC. I have to say I'm not comprehensive, it's just simply not possible in the hour, but it gives you sort of the snapshots of some of the things that have been identified as leading technologies. Essentially, we're trying to give you an overview of how the research is organized for nuclear power INC by the federal agencies, as well as a roadmap to the future. You might notice that I'm going to go kind of far afield from INC for a while. The reason I'm going there is that DOE does not have a specific INC research program. So you have to draw back to where are their technology research programs and say, how does INC relate to this? And so we're going to be talking about where are these where are the general research programs, and how do we get an INC component in that? The NRC, in contrast, does have a regular updated INC research plan, as well as even a digital INC research plan. We'll talk a little bit about why a variety of people there's several of folks who are former ANS presidents, several leading faculty in the nation, as well as the national lab staff. We're trying to get a cross-cut program because we think it's a good idea. Then just give you some examples of some current technologies under development. First, the big picture. This is DOE NE and how it's got its research program organized. First thing is the Nuclear Power 2010 initiative. This is the thing we're trying to get first sets of new plants built. Whether you've seen the new things at Constellation Energy or Old Dominion or Duke, there are several of the New Start consortium we're trying to build, whether it be an EPR or an AP1000. This is the place where they're trying to do things like look at new sites, developing the business case as to why a nuclear building the next reactor is a good idea. Looking at demonstrating the new NRC construction and operating licensing process, and as well as the early site permit process. The Advanced Fuel Cycle Initiative. We'll talk considerably about this because Traditionally, in a nuclear engineering program, the fuel cycle outside of reactor operations doesn't get as much attention. And yet, if you look at the technology requirements for this part of the nuclear power enterprise, they're pretty extreme. They're very high temperatures, very complex sets of interrelated processes, and much of the technologies, things like condition-based maintenance, wireless communications, which are very current in nuclear power INC, are very applicable to nuclear fuel reprocessing. Generation 4. Do a quick overview of what the Generation 4 reactors are, how much the DOE is spending on them, what their current sets of plans are. I won't even touch on the nuclear hydrogen initiative. That really doesn't seem to be very much headed for significant ongoing funding. This is a sort of the map of how DOE has arranged the boxes. First thing to note is that Shane Johnson, who is the head of currently NE1 acting, is acting. Since Bill Magwood resigned in May, they have not gotten a new NE1, and this indicates there's some possibility in the energy bill where the Department of Energy may elect to raise the status of nuclear energy, and until that's decided, chances are he's going to remain acting. Below him in May, John Gross was brought in, who leads all the research programs. Those are the two people to whom everybody else reports as far as the research programs. Buzz Savage leads the Advanced Fuel Cycle Initiatives, and Tom O'Connor leads the Next Generation Systems Development, which includes both the Generation 4, the international and national nuclear energy research initiatives, as well as the Nuclear Hydrogen Initiative. Down below, where all of the technology work is done, this is all part of the national labs. These are all staff members at national labs. So the technology decisions as far as which particular projects are selected in a large part by essentially a committee that is composed of the national lab technology experts. Okay, Generation 4 systems. Why the heck are we doing Generation 4, and why do we need INC as tie into this? Really trying to look at reduced capital costs, improve safety, reduce potential for proliferation. We'll talk some more about reduced potential for proliferation, why this is very important in the advanced fuel cycle initiatives, minimization of waste throughout the fuel cycle. And these are the 6 selected types of reactors: the gas-cooled fast, the lead-cooled fast reactor, the molten salt, the sodium-cooled fast reactor, the supercritical water, and the VHTR, very high temperature reactor. The first priority of everything is right now in the Gen 4 is to get the next generation nuclear plant running. This is currently envisioned to be a very high temperature reactor of some form. And longer term, we're still looking at closing the fuel cycle. Closing the fuel cycle means some form of a fast reactor. And much of this is being done internationally. I'll just do a very quick mention of these things. They're not all equally treated by the DOE. This very high temperature reactor gets well over half of the funding and well over half of the emphasis throughout the DOE program. It's a very high temperature reactor, and the picture that's drawn up here is a gas cooled, intended to be a helium coolant. It's actually now down to about 950 C coolant outlet temperature. It looks very much, it's a prismatic block fuel design. Looks very much like the GTMHR that General Atomics has been promoting. It is also well suited for hydrogen production, and that is part of what's being shown. Supercritical water-cooled reactor is very much going downward in funding. It does exist still in the process. It turns out it has some fairly challenging stability questions to it, and it does not look like this is my opinion, is likely to be a very long-term pursuit technology. Again, it is just basically water that's supercritical as a coolant, otherwise much like a light water reactor. Molten salt reactor, I believe, is getting something like 40K of funding this year. We'll tell you where this is in the priority list. Essentially, molten salt reactor has dissolved fuel in the molten salt, which is the coolant, and when it comes into the pot, it becomes critical. Essentially, there's enough money there to somebody to answer the phones and say, yes, there's a molten salt reactor program. That's it. Gas-cooled fast reactor. Oh, it's got some money every year. The problem with a gas-cooled fast reactor, and why it doesn't seem that it's growing that much, is that the reason people want the gas reactors is their passive safety. It's got all this graphite. The accidents take a week to occur, and it's very simple. The control is simple. All of the feedback mechanisms are so simple. It's very difficult to do anything wrong. Well, you give that up in order to get a fast reactor because you have to get rid of the graphite because it ceases to be fast if you have this huge mass of graphite. That means that you have the problems inherent with gas, i.e. bad heat transfer, which is a very bad idea for a power generation system, and yet you don't get the advantages of the safety. So yes, this continues just because we want to close the fuel cycle, and they're sort of covering their bases because we've already studied, well, there was one intervening. Lead-cooled reactor has got some very interesting niche uses. People are looking at these things for 15, 20-year cores where you just deploy them into the ground and around in third world countries often. Envisioned perhaps there's options of doing this in places in Alaska where you're remote from the grid and very little infrastructure, and then you come back and you just plug into them and get about 15, these are the sizes, 100 megawatts. A lot of these things are even looking at smaller sizes. The nice thing about these things is they've got really good safety, very high negative void coefficients, and the questions are, these things are very corrosion sensitive. Most of the work is going ahead and figuring out how to avoid lead or lead bismuth from corroding away your alloys. So things like corrosion monitoring get very interesting in this. The Russians have built 7 of these things for use as submarine reactor cores, so there is some real industrial history. Then this is the other fast reactor that's really been looked at, and it's not undergoing a great deal of research at the moment because, frankly, we have done this before. The sodium reactor was essentially last time was the GE Prism reactor in about late 90s and late 80s, and before that Clinch River in the late 70s. And it will be somewhat difficult for the government if it does decide to close the fuel cycle, because the last action anyone has taken in fast reactors was to drill a hole in the FFTF vessel so that you couldn't restart the fast flux test facility, and that will be a several $100 million mistake someone has to admit to. The questions you always end up with, the same with the fast reactors on these systems, is that if you get a large reactor, you can end up with positive void coefficients in them, and positive coefficients are a very bad idea in safety. And so again, questioning whether we're going to get this is a fast reactor model. This actually is something that, if you hear anybody from ORNL talk, will get promoted fairly heavily. This is ORNL's baby. Actually, Charles Forsberg is the lead inventor on this. Essentially is using molten salt as a coolant, but for the VHTR. So it's the same VHTR core. It's a thermal spectrum reactor. It's got very nice safety characteristics. The things that utilities really like, that's the little size. There are real possibilities of going significantly up from here, but that's the first target, is 1,300 megawatts, 1,500 megawatts, very nice large amounts of electrical output, very good passive safety. It's low pressure. If you're like 50 psi or so, you can use much less expensive materials. Containment requirements are really significantly reduced. The fuel requirements on this are 3 orders of magnitude less extreme than in the gas reactor, because in the gas reactor, if you don't, they're intended to blow out the original high pressure system, and that means you have to keep the helium very, very clean to be able to just vent it initially and then seal the containment. This low pressure to begin with. You can afford much cheaper fuel that we probably know how to make. I could spend a great deal of time on that, and I'm liable to if nobody stops me. So the Nuclear Power 2010 program then Essentially, this is the place right now where much of the action is, not so much from DOE, but from the industry perspective. People are lining up sort of as to, are we going to get an early, where are we in the early site process? Where are we in the construction and operating license process? The NRC is gearing up, hiring staff, spending a great deal of effort because it's quite concerned that several people are going to be applying for construction and operating licenses within the next 6 months, and it's just not staffed and ready for that. Essentially, it's focused, I would say, regulatory and institutional challenges are an awful lot of this, and and the next couple of slides will talk a little bit about how that's organized. Essentially, looking at sites for new plants, testing the early site permit process, and the construction and operating license process. A lot of these things have very significant INC components, and when we get to the second half of the presentation, I'm going to talk about this. This is just trying to lay the groundwork as to where is the funding, where are the national research directions. Developing new light water reactor designs. For example, as part of this thing, Westinghouse is on record as saying that if somebody orders an AP1000, the INC design is on the critical path because they've got it. While they've got a generic reactor safety, generic reactor approval, they don't have a specific reactor INC system. They believe very much that you can use conventional known technology for this, but somebody's going to have to do that in a fairly short order. And they would kind of like to use best of breed and best of breed technologies on top of that instead of just shoehorning in what they've currently got, and that's going to mean there's a research program. The Advanced Fuel Cycle Initiative mission is to develop proliferation resistant technologies. We're trying to get to a closed nuclear fuel cycle. There are a variety of reasons for that, but right now, say the technology focus is on spent nuclear fuel treatment and transmutation technology. Primary goals really to look at enhance the repository performance. Essentially, Yucca Mountain's already full as we have defined it, or will be very shortly, even though, and it's not open just from the fact we've been running reactors for more than 50 years, and we have 50 years of spent fuel already accumulated. We like very much not to have a second and a third and a fourth Yucca Mountain. The political fight for one was adequate. Essentially trying to look at, the other thing that they're looking at is different types of fuel forms. This is where the TRISO fuel for the high temperature reactors and nitrides and metallic fuels are continuing to be done. If you look at the budget, the AFCI's got a fairly large budget number sitting against it, but you have to kind of look a little bit further into there and see there's a great deal of set aside in there for cleaning up things like EBR2 fuel that is no longer used. And so the AFCI has got about the same size research budget as the Gen 4 program, both of them about $45 million. And those are pre-Katrina numbers, and heaven only knows what we're really going to see in this year. The other thing is really trying to do with the non-proliferation. Reducing the inventories of civilian plutonium is a very big deal at the moment, and there may be some significant changes coming up in DOE's programs to try to eliminate or reduce the amount of plutonium in civilian hands throughout the world. Closing the nuclear fuel cycle, though, is driven by non-proliferation environmental stewardship. If anybody does a quick economic model, and there have been several people who've done fairly detailed ones saying that, well, closing the fuel cycle costs money. Well, it sure does. You have to build this fancy recycle plants, and you've got to build new generation of reactors, which are probably not going to be as capitally efficient as the best of the light water reactors. With this new and that just basically means it's going to increase the price of nuclear generated electricity to close the fuel cycle. It does not, you can't really make the case because frankly, most of the models for the amount of uranium that's around and with low enrichment uranium is we have an awful lot of it, and it's going to last for many decades, probably a century or more, before we need to go to this for economic reasons. The reasons people are interested in it are essentially reducing the amount of plutonium at civilian sites and generally trying to get rid of the actinides from the waste stream. That is something which both is important for Yucca Mountain with the new rulings that we have to watch Yucca Mountain for that between 10,000 and 1 million years with the extreme extension of the life of the amount of time that Yucca Mountain has to be monitored. as well as just the general idea that it would be very good to have an industry where in less than 1,000 years we are reducing the total amount of radioactivity in the world. We're essentially decreasing the amounts of radioactivity instead of increasing it. It's another one of the eye charts, but this is actually this is the key sort of chart from the from the AFCI. It shows you the different paths for recycling and fuel recycling and where it's likely to be headed. Essentially, today we've got the spent fuel from commercial plants goes directly to the repository. We have conventional reprocessing heading into the PureX. Problem with the PureX is it separates out the plutonium and the uranium separately. So sometime in this in the fuel cycle or in the plant, you've got a purified stream of plutonium. While that's only one of these and it's in a very controlled area, currently politically that is not considered an acceptable, so we're looking at advanced proliferation resistant recycling, which separates out the plutonium along with the neptunium and uranium at the neptunium and americium at the same time. If you end up with enough neptunium and americium with the plutonium, it makes nothing except very, very challenging INC problems, because that's remote handling writ large. As a matter of fact, we'll talk a little bit later about the problems the Japanese have been having with the remote handling and how much you can end up making a recycling plant cost. The uranium comes out separately. Essentially, the only thing eventually that goes into this, essentially goes into LWRs for burning, and you need about one fast reactor for every 6 LWRs to end up burning up some of the actinides. But the model is the only thing that goes into the long-term repository is the fission products in a vitrified form. And as I said, in 1,000 years or so, we're intending to make them less radioactive than the natural uranium that they came from. So I'm pointing out this is what the AFCI is really doing. AFCI is doing things like looking at post-irradiation fuel. These are just specific details on there, things like actinide-bearing metallic and nitride fuels radiating the ATR. So they're into detailed technology pieces. When you're into detailed technology pieces, you have to look very down into the program and see, where do we apply? Where does INC really come into these pieces? 5 main research elements on here: separations technology, advanced aqueous processing. Aqueous processing is a fairly complex, many-layered plant. The estimates currently, I think the Japanese plant was $18 billion as there. You look at the amount of money in there and the processing, and then you look at things like the people who have been doing this for a while, the British at Sellafield, at the Thorpe plant. They have horrible online performance, or at least had until more recently, and a lot of things like condition-based diagnostics of basic process equipment, which are kind of unique pieces of equipment, things like fuel choppers that keep breaking down, which really have limited their long-term performance throughputs, which has effectively increased the plant cost dramatically if one of your major unit steps keeps breaking down. Other things are advanced fuels development. Mostly this is either high temperature fuels, which is the triso fuels. Again, something we don't know how to make, and process control would help. We know how to make them, but not with 1 part per million failure, which the very high temperature gas reactor requires. And things like systems analysis, and considerable amount. This, you might notice, a very significant fraction of the budget ends up in Las Vegas for reasons that Yucca Mountain is also in Nevada. And the NRC now. NRC actually has an INC research program. And if you go ahead and look at where they're headed and what they see as the major trends, you can look at essentially where things are going, because part of the NRC's mission is to stay abreast of where the emerging technologies are, because if somebody proposes to put one of these things in a nuclear reactor, they have to know how to respond in a regulatory sense. Major areas, systems aspects, things like environmental stressors. You simply get different failure modes out of digital systems than you do with analog systems. You may get a stuck thing, but you don't get race conditions. There are just digital systems provide extra complexity, and looking at what are the additional failure parts in things like an operating system in an analog control system. And complex systems give you additional complexity the NRC has to be aware of. Software quality assurance, exactly how you go about defining what that you've got quality software and not just a quality process for developing the software is major part of their research area. Some of the things then they try to stay abreast of the emerging INC technologies. One of the things is predictive maintenance and online monitoring. You have several faculty at this university who are quite well known in that area. Advanced instrumentation, smart transmitters. I'm going to mention wireless communication pretty heavily. NRC's got to focus on that, and the rest of the nuclear industry does, as well as OR&L, very much trying to avoid laying wires, and has different impacts on nuclear reactor safety and reliability. Things like, well, you can't really set wireless on fire, so you can't really cut the cables, but sometimes it might not be there because somebody who's moved a big piece of metal in the wrong spot. And they're just different implications. Computer security is probably the hottest research area. So all sorts of things. You can't really mention wireless without security in the same breath. And other things, risk assessments. Trying to go ahead and say, NRC's new mantra is risk-informed regulation. Well, risk-informed regulation means you have to be able to understand what the risks are. How do I numerically quantify these things? How do I put this thing into some form of a probabilistic risk assessment? Well, going ahead and figuring out some form of an assessment method to do and put this into for your PRA is a significant NRC research area in INC. Okay, now we get sort of into the why do we do this anyway? Why have a nuclear power INC research program? Because they've got these technology research programs, and in a large part you have to say, we've gone from 58%, I think at the low point, plant availability to something like 90% or 92% at different times plant availability. This happened with today's technology. It is not with tomorrow's technology, and research is about going ahead and bringing in tomorrow's technology. You have to have some reason why to go spend this money on a nuclear power INC research program. Well, part of the things is that there are things that the nuclear power industry is still trying to do. Things like close the fuel cycle, raise the efficiency, lower the capital costs. All those types of things are vexing problems. INC is deeply integrated. It may only be 10% of the plant cost, but if you look at the operations, how many trips and how much of the operations budgets are associated with the INC, INC in general needs to be thought of, in my opinion, about a third of the difficulty in the nuclear enterprise ends up being in the instrumentation and control somewhere. And yet we don't have a sort of a set-aside slice of the pie, much like fuels does or materials do. All the components then within the nuclear energy cycle, all of these things like high temperature process measurement and control, valid for the new high temperature reactors, valid for the advanced fuel cycle initiative. Each one of these valid for, that means both the fuel fab and the reprocessing center. Optimal equipment maintenance. As I pointed out, this has been a bugaboo throughout the nuclear enterprise. There are lots of big process equipments in this. We're a major industry. Secure information networking is very important if your primary instrumentation system, your primary control system is vulnerable, your plant is vulnerable. While future generation plants are intended perhaps not to have safety channels because we have full passive safety in them, it would still be a good idea to be able to operate your plant without somebody else getting involved in it. And then radiation effects on electronics, something which is distinct to the nuclear industry. Other people do high reliability electronics. To some extent, the military and the space people are also doing radiation tolerant electronics, but the nuclear industry's got its own particular needs, like lots of fast neutron flux. Now I'll point out, other people have been looking at things, is just saying that digital INC systems currently, this was something that one of the NRC staff said it's not his own, not an NRC opinion, but he looked at the licensee event reports, which are the things that the operating power plants have to file whenever they have something goes wrong. I wanted to see what fraction of the trips, what's going on, are related to INC. Well, this was specifically digital INC. You see, in this case, he was doing a study in 2000, and between 94 and 99, roughly an eighth of the trips involved digital INC. Nicely evenly divided between human systems interface, hardware, and software approximately, but it's still something that people are quite concerned about. I mean, tripping the plant is a very expensive thing to be doing. Okay, regulatory uncertainty. Why? The other things that INC can really help in the NP 2010 sense is how do we go ahead and get this next plant built? Well, that regulatory uncertainty, lack of confidence in the one-step licensing process, financial uncertainty in how much new plants cost and how long they will take to reach operation. The other things about nuclear waste disposal and accident indemnification. But the inspection testing, I think that's another slide, parts of these processes about demonstrating that we are adequately compliant in our construction. Well, how do you do that? A large part that's instrumentation. This is also information networking to say that I have complied exactly with my approved design. INC is again, economic competitiveness is in the power generation side of things. When you're trying to go ahead and running the plants, trying to keep lowering the price, yes, natural gas prices, our competitors are going through the roof. Coal is likely to probably get somewhat more expensive as we finally apply some more environmental regulations to it. But throughout the plant, INC systems really impact the operating costs. Plants aging and obsolescence gets preached very heavily. It is really a big deal. If you talk to somebody, actually go to the plants and you ask what are you doing? Well, they'll do things like, well, we're going to buy 30 years worth of these boards because I don't ever want to deal with again. And you just go look at the stocking system that they have. Yeah, they've got ways of going around things because they've had problems in the past. That's certainly not an optimal way of doing things. Is having a one-time buy for a plant life. And some of the maintenance on these things is just getting incredibly costly. Construction and maintenance simulation. One of the things that is really important in trying to lower the cost of things, because so much of a nuclear plant's cost is in its capital, is proper data visualization. Going ahead and this happens to be inside the AP 1000 where someone is doing a maintenance simulation. Most people are doing some estimates, whether it's EPRI or Westinghouse or EP or Framatome, about how much they can save with just from doing better data visualization and better plant simulation visualization. And it's about 30% of the construction schedule. That's pretty impressive if you look at how much you have just spent and what it depends upon what your overnight capital costs are, how much the savings are. But it's a very significant part of the cost of your plant. Is in can we go ahead and build this thing faster? Let me see if I can exit this for a moment. Let me see, how do I do that for exit?
Exit. Where do you want?
Yeah, I've got a movie that's behind this. Okay. Well, I'll keep talking while someone else figures this out on this. What I've got is Areva has got an example of some of its technologies that it's got that it's using for building the EPR. And what I wanted to do was show you briefly one of the Areva movies that they've got.
Turn it around, David.
Oh. While Areva's got a better construction movie, but that wasn't okay.
There we go.
They've got a better. What this is showing you is the degree to which, even in their basic demonstration of the plant, that data visualization is now just absolutely core to the ability of seeing how the plant is operating. This is just it's about a 4-minute movie on how to see where the EPR is. This happens to be the one that Olkiluoto, I'm learning to pronounce this. This is in southwest Finland that is being constructed. And you can see all of the different parts of the reactor. It becomes very obvious where the safety features are in, how the plant is done. Hopefully the next time I come and I can put on, they have a very detailed movie actually which shows their construction schedule about down to the level of the bulldozers moving and the cranes coming across and how you do all the planning. It's a very impressive piece of work. This is actually a pretty good though of showing a lot of the major safety features, and is one of the things that in any parts of the licensing process of showing the public what's going on. Things like they actually have the double containment structure, the location where you put, they've got this is where molten corium, if you melted the core, would flow out, the huge amount of extra suppression water in the reactor. All these things become very obvious when somebody's got a nice little 3D visualization model, which is just given out. Again, this is the corium. Unfortunately, of course, this is done by Kojima and Framatome, so everything is in French. That's the emergency cooling water. They do have an internal spray system, the spargers, and again, the double containment structure becomes very obvious here. That's a post 9/11 invention essentially, where they're trying to go ahead and if somebody runs a very large plane into this, to stop it in the first containment and then not present a challenge to the second containment. It's an interesting way of going at this, and perhaps other people may at some point also decide to go with a double containment or decide to go underground. I don't think they've run the new Airbus, the huge thing, into it computationally yet. And we'll go ahead and we'll go back to PowerPoint. That's just was just trying to show you some of the immediate value that the companies are seeing. There are, if you go to many of the different universities, I believe that one is at Penn State. There's some at Valparaiso. There are a variety of places that are doing very impressive amounts of visualization in direct support of nuclear power. Online instrumentation and condition-based maintenance. These types of things are now getting to be a really big deal. If you look at the amount of money which is involved in the current maintenance, well, we have one of our local companies which makes its entire business, AMS, on going ahead and doing that much of the maintenance for the pressure transmitters and the temperature transmitters in nuclear power plants. We have several of your faculty who have made much of their careers on this, on going ahead and looking at condition-based maintenance, where we're trying to go ahead and do things like saving the maintenance resources, reducing the amount of personnel dose. Other thing you can get is trying to get a power-up rate. People, I think the highest one so far has been granted was 17%. It's a pretty darn impressive amount more power just from these are improving much of their instrument accuracy. Though in most cases, frankly, there's a 2% margin that you may be able to recapture with instrument accuracy. Power up rates have been very involved with this. Essentially, though, focusing on increasing the plant availability and focus your maintenance resources. And current research area. We've got all these fancy numerical methods in for prognostics and diagnostics. Nobody can say numerically how good they are. If somebody wants to go ahead and get relief from the NRC saying, I have to calibrate this thing this often and I have to look at this thing and what's my surveillance intervals and such, somehow we have to come up with a way of characterizing the uncertainty. to say this is what the bounds are on the capabilities of my system. That's an important thing if prognostics and if this type of condition-based maintenance is actually going to win widespread introduction. And ITAC. I mentioned this briefly earlier. This is something that is for the NP 2010. This is likely to be a big deal in the next 5 years or so, perhaps longer, where does the plant as built adequately correspond to the certified reactor design? This is the only thing which is left as far for an intervener to say after all the money has been spent and an interest is clocking away before somebody starts selling watts out of the reactor. This is the big question. Did you build what was licensed? Licensed. We need to have an assured process for doing that. We did indeed build what was licensed, and somehow that's going to be a very involved data structure. That's going to be a lot of data recognition, and then say it's the only thing that has to come later. And then try to establish to the NRC legally what is adequacy. And the NRC will reach a regulatory position which says this is what is adequate. Somehow the NRC is going to need help with advice on, okay, how is this adequate? How did we prove this? What was good enough? Good enough. Those are the types of things where there's current research going on, and where there probably needs to be considerably more. Other things are, as people introduce new sensors, people introduce emerging or introduce wireless networking or new technologies. These all have regulatory impacts. Anything which has a regulatory impact, the NRC has to be prepared to deal with. Right now, the research objectives on here is to go ahead and help the NRC make future regulatory decisions by staying up to date. The NRC generally is interested in any time somebody's got a major change in the way that business as usual has been done, because they have a model for, we have light water reactors, they are done with analog, now slowly going to digital INC systems. There are certain sets of materials involved, certain sets of turbines. They know the system. They're working very well right now, but you make changes to that, the NRC starts being very much less comfortable, and frankly, currently they're staffed and organized to regulate the existing reactors in the existing form, because there's been a 20-year hiatus since they've been in the business of putting in new technology in forms of new reactors. That means the NRC is not quite as aware, and they're very concerned about this institutionally. Major reorganizations of their structure, trying to staff up and bring in consultants to help them be capable of dealing with when somebody's putting a new plant request in place. The NRC does periodic surveys, and I just got a copy of their emerging technology report. I've helped write it in the past, where you look at which technology areas they think are advancing and really worth monitoring. I've just grabbed, these are just some sample technologies, as I mentioned earlier. I'm not going to give you a comprehensive list of advancing INC areas. It's just, that's an enormous list of things. These are some of the things the NRC is looking at as key, though. Sensors and measurement systems. Communications and networking, microprocessors and other integrated circuits. These are sort of some of the obvious things that with the advent of the digital age, the nuclear reactors are very significantly behind the times. Much of the technologies is from the 50s and 60s, but new technologies, you can't buy 50s and 60s technologies for 2010 plants. They just don't exist. So these types of things are they're really starting to bring more modern, meaning things probably from the 90s, but much more modern technology into the plants. Computational platforms, PLCs, triple modular redundant controllers, diagnostics and prognostics, different forms of control and decisions. I didn't mention human system interactions, and I'm not going to, that was sort of one of the things I chopped off of my talk, as that's normally considered as part of, or is along in parallel with INC, as human-machine interface technologies, but it just broadens the scope of things. High-integrity software is certainly another very active research area. As we get more of our foreign people, competitors, Framatome, and you look at how they're running their N4 plants and how they're planning on running the EPR is with almost entirely digital systems, which means very much high integrity software. They're very different licensing regime process than the NRC is familiar with. Several new sensors. Some of these things are getting closer and closer to commercialization. Silicon carbide, replacing the fission chamber as the primary means of measuring the neutron flux, with a single channel instead of startup, intermediate, and power range channels. Fuel mimic power monitors, Johnson noise thermometry. They've each got slides later on. Some of these things are capable of going into the high temperature plants. The NRC says what the instrumentation for these high temperature plants is going to be very different than what currently exists, because much of the technology which is in the current plants simply doesn't apply to high temperature plants. There aren't any fission counters which can work above about 550 C that anyone's ever built. Well, if you get a core exit temperature of near 1000 C, you're going to have to come up with a new technology. Radiation hardened electronics. Progress is being made in some of these things, particularly by the space and defense areas. They've got things called the Rad Hard Design by Design coalitions that are trying to apply much better technologies into and perhaps even get electronics into containment. Would very much change how the reactors are run and designed if you could go ahead and you could reliably put electronics all the way into the containment. Silicon carbide flux monitor was the NRC selected as a leading technology. Essentially, it's a silicon carbide PIN structure with a lithium fluoride top layer. Lithium's got a high neutron absorption cross sections. You get triton comes out one way and the alpha particle comes out the other way when it captures a neutron. You generate your charge carriers in the depletion region of your PIN structure and produce current pulse. The advantage of these things is they're really fast, which means that you can get gigahertz type of responses. So that means you can get an extremely wide range response, and you can run them in pulse mode all the way up into the power range. The other thing they do is they're fairly hard to fast neutron damage, which means you can run them up to about 10 to the 17th NV 1 MeV equivalent, which means that sort of at the exit of the vessel, or perhaps even in a downcomer type region, you could really run these things for much of the life of the reactor. You also can get almost 100% gamma rejection, because the electrons, you get an electron generated by photoelectric or something. You just takes it doesn't deposit very much energy in this very thin depletion region. So you've got new technology, Westinghouse technology. They've been adopting it, and it looks like they're probably going to be putting this in some of their next generation of plants. Just quickly, fuel mimic power monitor. Different way of looking at things is essentially take a piece of fuel, put an electrical heater into it. If you go ahead and you just run a feedback circuit on this, where you go ahead and you measure the amount of power it takes to keep this chunk of fuel at a given temperature and where this thing is actually in the core, the amount of heat loss is a known property in this. Essentially, you can go ahead and at steady state get a measure of the total amount of power which is being deposited in that fuel mimic piece. Since that's actually what you're most interested in is the amount of power which is really being deposited there. So it's not a temperature, it's not a neutron flux, it's an energy generation monitor. It's a new technology. Ohio State's been has been very significantly involved in this. I think it's a little bit further from commercialization than the silicon carbide monitor. Johnson noise technology. Well, this periodically gets measured. There's some work going on even at UT on this, but ORNL's been involved in this since I think '73. It's such a good idea in some ways, but so technologically challenging. Essentially, Johnson noise is the random vibration of the atoms which represent temperature. You can actually watch the vibrations, which are the temperature, Well, you don't care what the property of your sensors are. If the resistance changes or some other property of the sensor changes, well, its temperature is what you were interested in. So if you're directly measuring the temperature, you've got a first principle drift-free measurement. It's a wonderful thing to have in a nuclear reactor where you've got lots of radiation, which is destroying the normal engineering properties of your sensor. Sensor is you get something which, okay, well, we don't care about that. The problem with this has been is that this is a very low-level sensor. When you're in the microvolt volt regions, you need a million-fold gain, very high stability. You also need very fancy ways of rejecting other forms of noise. There have been some very interesting technology developments with the advent of some of the digital signal processing to take advantage of the fact that Johnson noise is fundamentally white. All the interference sources are known to have known frequency characteristics, and just rejecting those band-limited noises has really proven to be very useful. It's only since about the year 2000 or so that with the speed of the DSPs, this has become practical to say that I want to have this in a normal chip. As opposed to having this in a very expensive DSP board. When we were trying this in about 1990, it was better than $15,000 a channel just in the DSP chips. NRC is also really working on wireless. Wireless is a big deal right now, and I've got a few slides on wireless that it looks like I'm going to have to go over very rapidly. Wireless data systems in nuclear plants. There are enormous amounts of cost in running wires in nuclear plants. In addition, life extension in nuclear plants, looking at the fixed systems in a nuclear plant. Well, the wires are one of those systems which age. If you've got an aging system, well, we'd like to avoid having to go ahead and rip out all the wires and put in new ones if you've got problems with the polymers, which are the insulation aging. And wireless is one of the capabilities of doing this. That brings into all those things about security, EMI, electromagnetic interference, radio frequency interference. It's actually happening. The picture at Comanche Peak, South Texas nuclear, where it's actually got a wireless vibration monitor installed running in a nuclear plant. No, it's not in a safety system, but it is running in a nuclear plant. Reasons things happen again. That's a pure estimate, but $2,000 a foot is a ridiculous amount of money to string wire, and that looks like what some of the estimates are on how much it costs in an established nuclear plant to put in more wiring. Current wireless systems are at about $1,000 a point per year in a nuclear plant. We really need to lower the cost about a factor of 5 yet before you're going to see people starting to deploy these things. And what you really need to do is get Moore's Law involved in this thing, and that means that you're going to need a sustaining ability of people to sell into this market, where they can look at, well, next year I'm going to need to buy more in this process, and the next improvement in this. Well, that has been driving the computer industry to better and better. And if we want to get into this regime where we're going to get a truly improved wireless network, that's the type of technology where we'll need to be headed towards. Last thing, one of the last points I'm making is, where is the next generation sensor systems? We go ahead and talk. A lot of INC is moving information around and moving data around, whether it be acquiring the information, something like a thermocouple, or whether it's the network, which is piping the information around. We're trying to go from data to information to knowledge. First generation systems, dumb. Thermocouples. You pumped voltages up to the control room. All sorts of sensitivities to all sorts of interferences. No intelligence in there. Second generation systems have fairly hierarchical. There's a localized some data checking within the system, but there's some supervision up to this, but a very fixed, and in a large part that's where we're headed to right now, is something which has got a hierarchical data-oriented a task-oriented looking at, well, this is pressurizer control. Next generation networks. These are the third generation systems, are these dynamic, reconfigurable types of systems, which are going to say, hey, what's my goal? If each part of the network knows the overall plant goal and how it serves as part of that system and can adapt itself so it helps to achieve the overall system goals, that's a third generation network. And then in concluding things, INC is really deeply involved with getting optimal performance throughout the nuclear energy enterprise. Secure, reliable data information really is a core for all nuclear power plants. And I've just got the listing of a series of the major technologies which are part of these things, whether it's advanced sensors, wireless, diagnostics, prognostics, I consider part of that, remote control and handling. Big deals, particularly in very highly radioactive materials. You don't want to get anywhere near them ever. Multi-unit controls. Several of the one of the NP 2010's candidates is the IRIS reactor. These things, when you're talking 400 megawatts, or some of the gas-cooled reactors, which are relatively small. Well, I've got 6 units on one site to make sort of one power plant. Figuring out, well, I built one of them and it's starting to run, and then I've built my second one. Well, I want it to run the same control room, and I'd kind of like not to shut down my first reactor while I'm building my second one. Figuring out how to do some of those things with shared services, shared networking. And then if I've got all my reactors running, and maybe I'd like to be doing desalination with some of them, and perhaps I'd like to be producing hydrogen with other ones, and maybe I want to change during the night to producing desalination and producing electricity during the daytime depending upon my economic conditions. Well, none of those things are very well known how you approach that. Those are the things that multi-unit control. Radiation-tolerant electronics, bringing process measurements right into closer to where things are happening. Assured quality software, having the ability of introducing digital systems into a nuclear plant with a known type of a schedule. This is exactly what I have to do. This will be acceptable. Acceptable is essentially where that's coming from. Data visualization and simulation. Understanding the vast quantities of data which are coming out of all these measurements and being able to do something with it to decrease project scheduling, decrease the amounts of worker dose. All of these things are very important. Compliance demonstration. Again, the ITAC keeps coming in. And then system autonomy. Many of these, as pointed out, the lead-bismuth reactors are envisioned to have very minimal supervision and run for quite a few years with almost no staffing. There's one of the smaller ones of these is being considered in Alaska to essentially run with basically no one there for about 10 megawatts, and that just produces an entirely different operating regime if no one's there watching it. And I've now spent the hour, and I thank you guys for your attention.
Okay. We have time for maybe 1 or 2 questions. Martin? Wait a minute. Let me give you the mic.
Can displacement cascades associated with neutron radiation damage mimic Johnson noise in the sensors?
We really don't think so. Johnson noise ends up being an extremely wideband phenomenon. It's actually white out into the gigahertz region. If you could go ahead and, if you were giving it a sufficiently high dose to give it anything other than that being an extremely tiny preferential spike, the thing would vaporize instantly. It's just not in the same, the types of regime. These things are collision densities in most materials are like 10 to the 14th collisions per second. So each one of these things is being involved 10 to the 14th times per second. You just don't get 10 to the 14th neutron interactions in a very small piece every second. The dose rates are it's not a possibility of being a problem.
Bill?
David, you mentioned smart sensors and radiation hardened devices. What is the level of participation by sensor manufacturers in developing these things?
Radiation hard, there are a few people who've had customized businesses involved in this. For example, Northrop Grumman has a plant that's right near the Baltimore airport, which I've forgotten the name of, but their entire business now is we've bought one of the process lines to produce specific parts, and we're going to produce the same ones for many years. We're going to use the best of the rad-hard by design technologies. There's enough money that people are doing sort of a specific people. BAE Systems produces the rad-hard PC. There are, but as far as widespread manufacturing, there's a little bit of involvement by people like Intel. The reason that there's involvement for that is that turns out transient upsets they're getting the memory cells small enough that they're starting to get transient upsets in their things just from cosmic radiation, which means things like you're having to do TMR logic in some of the higher density memory cells, just to and that's simply a part of they're getting smaller and smaller essentially storage capacitors. But otherwise, it's still a custom market, mostly feeding the space and defense industries.
Okay. I think we'd better adjourn now. We do have refreshments downstairs, and everyone is invited. But before we adjourn, let's express our appreciation again to Dr. Holcomb for his presentation. Thank you. That was excellent. Lots of good information. Yeah, it's not clear how to turn it off. So, Larry, would you take Dave on downstairs?
Certainly.